Today I'm going to look at the All Power's S700. This is a 700 watt portable power station using lithium ion technology. You can charge it from AC, you can charge it from DC, you can charge it from solar, you can even charge it from your USB-C adapter at up to 60 watts. We're going to tear this one down, take a look at the construction, take a look at the battery pack. I'll give it a full charge and a full discharge and we'll see how it performs. Let's check it out. This is a new power station that I just received to evaluate. This is some of the features of it. So it's a lithium ion battery. It's 164,000 milliamp hour, 3.7 volt, 606 watt hours. AC output 700 watts continuous, surge to 1400 watts. DC output, it's got 12 volt 5 amp and a 12 volt 10 amp car outlet. USB, 3 of them, 5 volt 3 amp, and a USB-C, which will feature 5, 9, 12, 15, and 20 volts with a maximum output of 100 watts and maximum input of 60 watts. So it can take input through the USB-C, it looks like, as well for charging. Let's open this one up, see what we get in the box. Consider this the official unboxing. Destruction manual, we don't need to read that, because these things aren't simple enough to use without reading the manual. Then what good are they, right? Alright, what do we got here? We got the power station. We got this box here, probably has cables and stuff in it, and we have the power station with a handle to lift it out. So that's what's in the box, and some silica gel. There's the unit itself. Okay, let's get a look at this unit from the front. First of all, I see that there's 2 LED lights on the front. It's got a power button, a DC button, and an AC button. On the side we have a DC input and a DC 12 volt. There it is, there's the DC 12 volt standard cigar type plug. On the other side we have 3 standard USB and a USB-C plus, as well as 2 standard DC outputs. In the accessory pack we have a charging brick and a power cord, standard power cord, and the charging brick here, its output is 20 volts at 5 amps, and this is for charging it up. So unlike some others, I will say right now without turning it on that this will not operate as a UPS because it does not have a 120 volt input. Therefore the inverter would always be operational, and whether it can provide full power output while being charged on a 5 amp supply, no, that's not going to happen. But what we're going to do on this is I'm going to charge this unit up, and we're going to load it down, and we're going to see how long it runs. We're going to put it through the paces like everything else that I do. So first things first, well, first of all, I'll turn it on. We'll take a look at what the charge is like on here right now. So if I turn it on, there's probably be a partial charge. Maybe there won't be. Power. Oh, there might not be any charge at all in it at this point. So it's capable of charging and discharging at the same time. I would imagine that's if you're going to charge it from solar, for example. I'm not going to bother with the Android or iOS apps, but they do have apps that you can install so that it will allow you to control it from a phone. Again, not necessary. Okay, so it says do use the included AC adapter. Another one might shorten its service life. And charging with the PD charger from USB on the other side, it supports two-way charging up to 60 watts maximum. So you can use a 60 watt, like a USB-C charger rated at 60 watts. You can charge it from your car. It says on here, we suggest only doing this when your car is running, obviously because you'll run down your car battery. Right? You need to have the engine running. But you can charge it with the DC input. And DC input so the DC input on either of these for charging up to 24 volts, 12 to 24 volts on that one. This one's for solar charging, as it shows here. Charging from solar And you can use a foldable solar power up to 100 watts, 18 volts, 100 watts. AC wall charger, it's 100 watt in. It says it'll take 5 to 6 hours. Carport will take 5 to 6 hours. A PD charger, like USB-C, PD adapter, 10 hours. And with the AC charger plus USB, you can actually charge with both of them at the same time, 4 hours. Solar panel will take 5 to 6 hours to charge. That's what they say. We got 3 USB-A and 1 USB-C, 2 DC for LED, 2 times DC for LED lamps and other devices that require more than 12 volts working voltage, and no more than 5 amps per outlet. AC output, it's a running power less than 700 watts. The initial starting wattage up to 1400. Built in with the AC sockets are built in with short circuit protection. Car socket for like onboard fridges and stuff, 12 volt appliances, and that will draw or provide up to 10 amps of power. But I guess I have to charge this first because I think it's completely dead. I didn't see any switch on here unless I missed a master power switch somewhere on here, which I didn't see. So I think it just isn't shut down because it's completely drained. So let's plug in the charge cord on the side, and it tells me that it's at 0%. So it's going to charge. So we're going to let this thing charge for a while here, and then we'll play around with it, and I'll take it apart. Actually, you know, I can probably take it apart right now that it's at 0% because it's going to take a few hours to charge. So let's tear it down first, and then we'll do the test, because I always like to try to tear these things down when there's no charge on the battery, obviously because they're a heck of a lot safer. If something were to short out, I would rather short out a battery that's dead and then one that's fully charged, which could create a lot of damage. So let's pull this thing apart right now. Now, people often wonder, what do I do with these power stations? Because I've done a few of them. I've done a few reviews. Well, I tend to put some of them in service. I've got a couple that I'm using. I'm using one as a UPS. I won't tell you which brand, but I'm using one as a UPS. I've got another one that I hang on to just in case the power goes out. And a lot of these units here, because I've got more than I need, I turn around and sell them to campers. And someone will get a good deal on this one once I'm done with it. That's the ones that I don't have to send back. Some I have to send back because they're just sent to me on evaluation. So to get into this one, there's 4, looks like they're hex keys on the bottom. It uses 4mm hex keys, so just get them going and then unscrew them. And that should separate the battery from the rest of the unit. I don't know whether the bottom lifts off it or whether the top lifts off or what, but we'll get the screws out. Now, does this lift off or does the top lift? Looks like the top lifts off, so let's separate the top. There is the top. Excellent. We can unplug some things here so that we can look at it. So let's unplug the AC output. That's that one. And we can unplug the fan. Everything's glued in here as well. But I should be able to get the fan off of this. Break the bond here on the fan. Here we go. Now I can separate the top cover. Okay. So nothing special there. Just 2 outlets. There's no ground. It's just a hole that you would plug in your 3-prong plug, but the ground doesn't connect to anything because obviously there's no ground on this. It's battery powered. None of them have a ground. So for safety, because this thing's flashing, so we know it's got juice, but there's a couple big connectors down here for the battery and so forth, so I think we'll just disconnect them, and that should disconnect the power. There, okay. Now it's sort of safe. But here's the battery. We'll just separate that just so that's for a fan. It's not I thought it was a temperature sensor, but it's actually not. It's for a fan right down here. So there's a fan on the top and a fan on the batteries themselves, which is good. Got fresh air on one side and exhaust on the other. Here's the battery pack. I know you guys are probably pretty interested to see what it uses for cells. It's got a bunch of cells in here. So first of all, let's measure the voltage on the battery terminals here. Now remember, it is not charged now, so there still will be voltage on the cells, so for sure. What do we have? On this connector here, we have 10 volts, and this other one probably doesn't have anything because this is probably a charging port. Oh, it's got 10, so they're both probably connected together, I'm gonna guess. One is a charging port and one's a discharging port, right? Yeah, you see, ground, and then positive and positive. So that's all that is. These are just connected in parallel. One of them's going to be charging. One's going to be going to the charging circuitry, and the other one's going to be going to the discharging circuitry. So I put it that way. Big cables are going up here to the inverter. This is obviously the power inverter because there's where the AC comes off there, and these other ones here more than likely just go down to the DC board here, and that is where they're connected. We'll separate these boards to take a look at the other circuit board. This has got the low voltage, the DC stuff on the little board on the bottom. This is going to be the inverter board. Let's just remove the battery completely. Should be able to remove the entire battery pack. Okay, this should lift out the battery pack, which it does. So here are the cells themselves. There's 40 of them. There's 8 of them across, and there's 5 of them deep. So 8 times 5 is 40 cells. You can see there's the 5 rows deep and 8 on the other side. 40 cells. They are, what are these ones? They're 3.6 volt, 15.8 watt hour cells, and they are 21700. Yeah, N21700 is the lithium ion cells, cylindrical cells. They're all going to be bonded, I guess, in series. Well, some of them will be in series, some of them will be in parallel, I'm sure, the way that they run them. That way you get the current up, right? So you'll have blocks in series and blocks in parallel. And if we were to open up this, if I take off the insulator on the top here, there's a circuit board on top here as well, though. This is probably going to be battery management and temperature control. Oh yeah, there's a bunch of components on here. So I think if I just open this up, cut this tape, I can stick it back down. So if I cut this tape here, I can probably show you guys underneath this. Without creating too much of a hazard. Okay, so glued down on top as well, but here's our battery management software. As you can see, there's more stuff taped down here. We've got a bunch of MOSFETs, or these diodes, and all these are these are MOSFETs, QD3, QD4. I think they're MOSFETs. I can't see the number on them, but anyway, battery negative, battery positive. I think the output on this is like 12 or 14 volts or whatever, and then there'll be a bunch of them in parallel with each other, and they're switched through this battery management software. Little chip here controls it. You can see battery 3, battery 2, battery 1, and there's probably another one. Kind of looks like there's 4 groups, like group 1, group 2, group 3, group 4, and that each of the cells are 5 of them in series. Makes the most sense. That would give you, what, about 14.4 or so volts when it's fully charged. That kind of looks like how it's wired. So you got 5 cells in series, 5 cells in series, and then these are in parallel. So that bank would be parallel, that bank would be parallel, that bank would be parallel, and that bank would be parallel. And then they can control the different banks here for charging and discharging. That kind of looks like the way that they have wired this. I'm not going to tear it down obviously any more than this, because even though the cells aren't fully charged, they still have enough current in there that if there was a short circuit to occur, we would have a major problem here. And lithium fires are not easy to put out. So I'm not going to take this down any more than I have. I'm going to actually put the battery back in. I just wanted to show you guys what the cells look like and what type of quality the cells are. And I think the cells are probably of pretty good quality. We don't see a lot of really shoddy lithium cells these days. Lithium batteries themselves are because of the danger involved with fires with poor quality lithium cells, no manufacturer that's selling a product that you're going to have in your house is going to put in substandard cells. That goes without reason because of the liability if there was a problem. And it's true, you know, we hear on the news of someone's e-bike catching fire, you know, and then we find out, well, wait a minute, they modified it and they bought themselves an aftermarket battery, and they added extra capacity so that their e-bike would go further. The manufacturer didn't have that battery on it. It was an aftermarket battery that someone decided that they were going to modify and rig up themselves, and then the battery caught fire because, of course, the battery management software was designed for a different battery. So I'm not going to take this down anymore. I'm going to throw this back into the case, and then we'll take a look at the inverter board, and then I'm going to charge this up, and we'll run some load tests on it once it's charged and see how long it runs and how much power I can draw from it. Next, we'll remove the inverter board, as I want to get a look at the other board underneath. Now, someone once asked me, what good are these units that don't have the AC pass-through? That don't have the UPS capabilities. A unit like this that does not have AC pass-through or AC charging, so that you can run devices on AC full-time, and the battery will kick in either as a UPS or as a standby. And there's different types. I've got some that are standby supplies where the AC just is passed through, and then if the power goes out or the power drops, the inverter kicks in. And then I've got other ones where the inverter is running full-time and the AC is just keeping everything charged. So there are two different types. But the big difference between the two, they're marketed differently. This is not marketed for someone to use as a UPS. This is marketed for somebody who's going to be living off grid, maybe in a camper or a motorhome or something where they want to have extra power, tenters or whatever. Or you got a cabin or something, you know, that you don't have power. You can charge it up with solar, and it'll give you AC to power some appliances and so forth. That's what the intended market of something like this is. And for people that need it, if their power goes out, they can have it charged. But this is not one that you would use normally for say backing up your computer and so forth. So this is a 110 volt 60 hertz board. It's listed right here. Here's we got some big copper, looks like copper, maybe it's brass, looks like, I mean, it doesn't look copper, it looks, I guess it is, but it just doesn't look the same. It almost looks like a copper alloy. But that's just to increase the current handling capability coming in here from the main power in. As you can see how big these cables are. These are, what, about a number 8, I guess. It looks about a number 8 gauge, either a 6 or an 8 gauge. It's they're pretty thick. So our power comes in. There's big fuses right here, right? That's what these are. They got glue on top of them, but those are fuses that are soldered down to the board. There's 3 of them. They're like automotive fuses. I don't know how many amps they are. It might say if I can see it, but they've soldered right down into the board, right there. Power comes in, goes through the 3 fuses. It's got protection, so if something were to catastrophically fail on the inverter, like the MOSFETs or something were to short, or there was a catastrophic failure on the inverter board, remember that the output is protected. So if you overload it, it's going to shut down. But if something were to catastrophically fail on the inverter board itself to cause a dead short on the battery, you wouldn't have to worry about this thing burning up, because those fuses are going to pop, and that's going to shut the entire unit down. Very important that you've got fuses on it. I'm glad to see that there's 2 fuses here. No, there's not a lot of separation between the 2 of them, but again, we're not talking high voltage, we're talking around 14 volts. So you're not going to have any arc over at 14 volts there. So here our main power comes in, ground on here, and our main power on this side, and this is going to go over through this big toroid and provide power over to MOSFETs. Here's a transformer over here, and that steps up our power to a higher voltage, 110 volts or 120 volts. Again, it's AC because this is going to be a high frequency oscillator. It's not doing it at 60 hertz. Guaranteed it's not doing it at 60 hertz. This is going to be an inverter style of power supply. So the incoming DC is changed to a high frequency DC to run through the transformer to give us our high frequency, higher voltage output, which is rectified here. There's a rectifier over on this side here, full wave bridge rectifier coming off the transformer. I guess this is the transformer right here, because I can see windings going into the primary side, and this is the secondary side right there. So here's your primary, and these are going to be the outputs, and they're going over to these bank of MOSFETs over here. So here's our bank of MOSFETs to switch back and forth. This creates the high frequency AC, or high frequency pulsating DC, I should say, which goes through the transformer, which gives us our 110 volts output. On the secondary of this transformer, you can actually see the windings here. So these great big windings here, these are the primary and these ones are the secondary. So how that works is your DC power goes in, right, from the battery onto these two terminals, one winding here, one winding there. They're going down and they're going into parallel, 3 paralleled transistors, MOSFETs. So they're switching one on, the other on. One's on at a time, one banks at a time. That creates a rotating magnetic field just because you're drawing current through one winding and then the other. And these will be wound out of phase. So you've got your north-south phase reversing from one to the other, which creates a collapsing magnetic field every time it changes direction, and you produce an AC signal on the secondary. Secondary from here goes down. You can see the outputs from the secondary here. It looks like there's a capacitor over here. There's a bank of capacitors, which there are. That's to increase your power factor. Your negatives come out here, go into the rectifier, and your DC voltage is created across the output here. AC in, DC out. Goes into your filter caps on top here. This is going to rectify your high voltage DC. This then is presented over to the pure sine wave inverter, which is this transformer and this, two transformers here, capacitor and your control circuit, to generate the sine wave signal, and that would be generated with these transistors over here. These will generate your sine wave signal and present that to the AC output terminal over here. This is the terminal there, comes off of this coil, goes through this conductor, and that is the AC inverter. Looks to be really well built. I'm impressed. I don't see anything of any concern here. Looking at the soldering here, it looks to be okay. Maybe a little bit rough there, but that's nothing really to worry about. Looks okay. So that's the AC side. This is the DC side. So that's the one that comes off this big, heavy cable right here. The smaller cable, this one here, goes to the DC board. This is going to have the charge circuit as well as the DC output. So, got DC to DC converters on here. They are going to set the 12 volt output, one going to that output, the other two going to the other two DC outputs over here. Got a buck converter, as this one's called. That's what these coils would be for, buck converter for 12 volts, and these ones here are going to obviously be for the USB outputs. You got the circuitry associated with the USB-C and the USB-A with its own buck converter. Display is on the front here, and you got some power buttons and so forth over there. Looks to have a Bluetooth chip down here. This is so that the unit can communicate with your phone. You can download the app and then you can log in and you can change settings and probably change the frequency from 50 to 60 hertz and turn on the boost if you want the extra high current, for example. Most of them you have to use the app for that. So let's throw this board back in. I'm going to put this back together and we're going to charge it and then we're going to test it. Before I throw it together, let's go over some of the safety features that we see on this unit. Like there's thermal detection over here, there's a temperature sensor over here, another one over on this heat sink. This is going to monitor the temperature of the heat sink so that if the unit is overheating, it's going to shut it down. There's 4 fans that I count. There's one here, of course, in the battery base that you guys saw before. There's one there. There's also one in the top cover. Remember the one that was up in the top cover there? There's a cooling fan there as well. And there's 2 more on the inverter board. I don't know if you guys spotted them or not, but obviously there's one there. But there's a second smaller one here, which is blowing air directly over the heatsink. So this one's blowing air over this is the sine wave generator. So one large fan here blowing air over the circuit board, over the transformers, and over the heatsink. And then there's a secondary fan over here, which is blowing air directly over the DC to DC inverter board, or the inverter transistors over there. So the thing should stay nice and cool when it's in operation. I'm going to reconnect the power connectors now, and then we'll put this unit together and I'll give it a charge, and then we're going to we're going to run it and see how long it runs for and how long it takes to charge. But first things first though, let me get the power cables connected again. It's lighting up. It's got power. I see green lights blinking on here on the circuit board internal. I see some green lights flashing away. So we know it's alive. It's waiting to be turned on or something. Plug the top fan back in. And the AC output. Alright, got the unit back together. I'm going to plug the DC charging cord in. It lights up. It tells me it's at 0%. We're going to time this and see how long it takes to charge. We'll see how long it takes. If we look at the display on the front, it's actually probably going to tell me the time it's taking right here. But we're putting in 15 watts in right now. I'm going to cheat because I can add an additional 60 watts from a 60 watt USB charger. I'm going to plug this in and we'll add another 60 watts, so this will charge it up a little bit quicker. So I can do that. I can plug this in to the PD charger and now it's increasing the power that it's charging. Okay, it's ramped up to full power now. If we look at the meter, it's showing me I got 160 watts going in. If I unplug the USB-C, it'll drop down to 100 watts. It was showing low before. I'm thinking probably because the cells were at the low state of charge, so it was bringing them up slowly, and now it's ramped up to 100 watts, which is the AC adapter. And if I plug the USB-C in, it'll go to 160, and now if I unplug this one, it should drop down to 60. So if I unplug this one here, it should drop down to 60 because now it's just charging from USB-C. There you go. 65 watts. That's what this one's rated, 65 watts. So I'll put the main charger back on and we will let this charge up. Okay, I've been charging for 3 hours and 21 minutes. I'm at 99% charge. According to this, it's been 3 hours and 19 minutes, but my stopwatch has been going for 3 hours and 21 minutes. And as I say, we're at 99%. So we're just waiting for it to hit 100. And then I'm going to plug some resistive loads in and we'll time it and see how long it takes to discharge. While I'm waiting for the charge to finish, you'll notice it has 2 lights, which can be operated independently. So it provides enough light to see what you're doing. It's like having a flashlight, right? So, close proximity work light. Okay, 3 hours and 32 minutes it took to fully charge the battery on both the USB-C and the the supply charger, which was charging it at the maximum power. There's buttons on the front here. This is to turn on the Bluetooth. So you can control it with your phone. You press and hold. And to turn on the DC power, you just tap the DC button. And AC power, you just press and hold AC. It'll beep, and the fans will come on momentarily to indicate that the AC inverter is running, and then they'll come on as needed when you are drawing power. To turn off the AC, press and hold. We'll try the USB charging. I'll try my USB-C cable. I turn on DC power and I plug my USB-C cable in. If I plug the other end into my phone, it should start charging my phone and it should tell us how many watts we are charging at. Which it is. It says fast charging 1 hour and 21 minutes to fully charged, and it's showing it's charging at 8 watts. Plug that one in. Unplug this one here. And plug this one here in. It now tells me it's charging at 6 watts. USB-A, 7 watts. What will my phone tell me? It should probably just tell me it's regular charging. Yeah, regular charging, 1 hour 30 minutes till full. And if I plug in this one, fast charging, 1 hour 20 minutes till full. That's the difference between the USB-C and the USB-A. To test the AC power capabilities, I'm going to use my heat gun. This is a 2-power heat gun, a 1350 watts on high. We'll turn on the AC power. Plug in the heat gun, and we'll start it up on low power. And we're going to time this too. I'm going to draw the full maximum power from the unit. We're going to time it and see how long it runs for. So I've got my stopwatch ready here. But if I turn on to low power, showing me we're drawing 545 watts. Now if I turn on the high power, I should max this out. Oh, so I overloaded it because I don't have this thing set for surge. Although it will let it start. So that's the shutdown. I can start something for an appliance that takes power to get going, but then it has to go back. We're going to start the stopwatch here. I'm going to draw this at this type of power, and we'll see how long it runs before it shuts down. Now this unit's rated at 110 volts output. We saw the sticker on the bottom. I'm measuring 113 volts under load. Let's just turn the load off momentarily to see if the voltage changes. We'll see the voltage is constant. What about if I put it into surge? Right, so it dropped to, whoops, I left it on too long. It dropped to 105 volts there while I was overloading it. But at this 550 watts now, I think that's what this draws on low. I should measure it with my other meter. I know it draws 1350 on high, but on low it draws, I'm getting 532 according to the meter on here. But our voltage is holding pretty steady here. Been going for 3 minutes and 15 seconds. Battery is showing 92% remaining. Output voltage 113 volts AC. Just checking the fans on the unit. It's drawing air in on the right side, so the fan on the battery is actually an intake fan. It's blowing air over the cells, and the exhaust is on the left side here. I don't feel any real warmth, slightly warmer, which is again to be expected. On the top side, this is the air intake on this side, and the exhaust is over here. So it's drawing air in. The two fans over the circuit board are drawing air in to blow air over the inverter. And then there's the exhaust fan in the top, which is exhausting it out the top. We're sitting at 90% now, 89%. It's been going for about 4 minutes and 45 seconds. We're watching the counter on here. It's showing 36. I'm assuming that means 36 minutes remaining. It's been going now for about 9 minutes, and we're at 80% battery life. Showing it was 37, it just dropped to 36. This should give me an idea how long the battery will run at this load. If I turn off the load, it should recalculate and tell me that I've got 89 hours of battery life at no load. Now if I plug in a small load, we'll just put something on that's relatively small, such as I'll plug my camera that generates color bars in. We'll just see what it shows for watts. So here, this one's drawing 17 watts, and it should last, drawing a 17 watt load, 15 hours and 34 minutes is what this load at 17 watts. So this is an actual indicator as to approximately how much time you've got depending on what you're loading it up with. If I go back to the big heavy load, it will once again drop down now to 35 minutes. So we're going to let it run on this load because I want to see how it performs, and if it will give me 35 more minutes of this load at full power. Because this is not just this is kind of a stress test on how long it's, or whether it's going to shut down, whether it's going to overheat. So I kind of try to draw it at maximum power. We're drawing about 528 watts, 29 watts now. I'll add my camera as well, and we're now at 546 watts because I just added the camera, right? So this is drawing 527, 536, and it adjusts the time accordingly. If I turn off, now you see we're down to 17 watts. We're back up to 15 hours and 4 minutes. As the goal is to try to load this to maximum, I'll add a 100 watt light bulb. Now we're up to 625 watts, so we're getting close to the 700 watt maximum on this. Okay, we're down to 7 minutes according to the guessometer. I've been running 26 minutes now on pretty much full power. And I've got the heat gun and a 100 watt light bulb running here, and the light bulb is still running pretty bright. It hasn't started to dim or anything. So it seems to be putting out pretty good, reliable power. At this rate, if it goes another 7 minutes, that's about 35 minutes total, I guess. We're down to 16%. I'm curious to see at what percentage the AC shuts off. Because the manual says that you can't run the AC if you're below 10% battery power. So I'm curious to see whether the AC is going to shut off when it hits 10%. Also, the top cover is getting warm now. Not hot, but warm. The air coming out of the vents is warm, and the top cover is warm, so we are certainly putting this unit under a stress test for sure. We're down to 14% battery life now, showing 6 minutes remaining, now 13%. So we'll see how accurate the countdown timer is. And it just shut off right there. You just saw it, 28 minutes and 50 seconds. It got to 10% and it shut down. Now the DC probably will still work, or will it not? Looks like it's not going to do anything. I can unplug the load from it. It is dead in the water. So the claims were correct. When it gets down to 10%, it shuts off when you're drawing AC power. And everything is now off. Oops, can I get the lights to work? Even the lights won't come on. It says 0. Just a little blink. Okay, I'm going to plug the unit back in and charge it up again. And that's about it for this one. So thanks for watching. We'll catch you in the next one. Bye.